Hello everyone, this is Kaveh in Honolulu with lesson 7 of our series of Common Lisp and OpenGL lessons. Um, so today we're going to cover colors, introduce the concept of colors for our graphics and how we might encode those. But before we do, I wanted to talk a little bit about methods and generic functions and classes in Common Lisp. So I think we've mentioned before that in Common Lisp, methods don't belong to classes. In languages that are derived from Smalltalk with single inheritance, part of the encapsulation is that the methods belong to the classes and are defined as such. And then the classes respond to those methods. And that's how you basically organize your code. So whether it's a text file like an Objective-C, you list your methods inside the class definition, or even C++, or whether you have an IDE like you have in Smalltalk, where your browser lists all the methods for you that belong to a certain class. But Common Lisp took the idea of methods and generalized them into generic functions by allowing multiple dispatch. So instead of only looking at the value or type, I should say, of the first argument in the method to determine which class it goes to, you can look at an arbitrary number of these. And I believe the Julia guys are now pushing that concept or philosophy for multi-methods and doing math operations and so on. But hey, Common Lisp had it 40 years ago. So I wanted to show an example of how we can, another alternate way of defining generic functions. We had the point multiply method that we had seen before, which basically took 2 points or took a point and a number and did the multiplication. So this is an alternate syntax for defining the same thing, where before, in the previous cases, we just defined 2 methods and the system automatically defined a generic function the first time we defined a method with a certain signature. But here we can actually wrap these all up together if we want to and say we have a generic function p star that takes 2 objects and has a method p star that takes a point and a point and does this. And then it has a method p star that takes a point and a number and it does this. So it's a way of perhaps wrapping up methods inside generic functions and organizing your files in that way. Whether it's better or not, I don't know. Out of habit and out of, having used other OO languages, I'm more in the habit of just defining sections of files having to do with classes and then putting the methods in there. But this is an alternate way of looking at it, and it's actually a good argument for having an IDE, which will allow you to basically, look at things by generic functions or look at things by classes and see the aspect of them that you actually want to see. All right, so that was just a little gentle introduction to some Common Lisp object system stuff. Pardon me. All right, so colors. When we defined our points, we used classes for pedagogical reasons. But for colors, also for pedagogical reasons, I'm going to do an alternate approach and use arrays. So our colors basically have red, green, blue, and alpha values, so it's a quad. And when we define a color, we're going to create a vector, and a vector is basically shorthand in Common Lisp for a one-dimensional array. Common Lisp, kind of taking the inspiration from Fortran, has multi-dimensional arrays up to level 7 at least. So you can have a 7-dimensional array in any Common Lisp compliant ANSI standard implementation. So that makes life a lot easier when you're doing matrices and things like that. It just takes care of a lot of boilerplate for you. But the vector is basically a one-dimensional array. And we do the similar thing that we did for the point, where we have a cbang constructor, and it creates a vector, courses everything single float again, because that's what OpenGL expects. When we pass OpenGL a color, if it doesn't see a single float, it'll complain with the way we're doing it. And then we define some accessors, very straightforward, kind of. Let's just call them C red, C green, C blue, and C alpha. And aref is the array reference in Common Lisp. So aref C0 is basically in C, it's C square bracket 0. And then we can define a destructive setter where we use the exclamation mark to notify people that it's a destructive operation that basically sets the values of color 2 into color 1. And then takes an optional key as to whether or not set the alpha value as well, which it does by default. Some mathematical operations and utilities on colors, color interpolation between two colors. So we had seen mapcar and mapc, but there's a more generic function called map that takes a type and then does the mapping across that type and returns a value of that. Actually, I don't know if map returns a value. I don't think it does. It's not important for our needs. So basically, this takes a function of two arguments, traverses two arrays, and applies the function to them, and returns the result. So crand returns a random color. crand with alpha also randomizes the alpha for us. crand2 randomizes a color between two values. C+ adds two colors. And cjitter basically offsets a color by a certain color delta so that we can randomize things. So let's select and evaluate all these things. All right, so that's done. Now, let's start using color. The first thing we're going to do is basically add a background color to our scene class. So we had a scene class before that had a list of shapes, and that was the only thing it had. But now, again, thanks to the flexibility of Common Lisp, we can essentially redefine a class and stay within our live image and not have to exit and restart everything. So we simply compile this. We have to modify the draw method to handle the background color. And I'm not going to get into the details of this, but this is some OpenGL stuff that needs to be done. Since colors have alpha values, I should explain what an alpha value is. Alpha value is basically the opacity value of the color. So if the alpha is 1, the color is completely opaque. If the alpha is 0.5, it's 50% transparent. And if the alpha is 0, it's 100% transparent. So OpenGL needs some boilerplate to be able to handle blending pixel values and things like that. So we just put that stuff in here. And then this is where we take care of our background color. So before we just set it to 0, if you remember. But now we check if the view has a scene, because this is a method on scene view, which is a subclass of an Objective-C NS OpenGL view or whatever it's called. If it has a scene, we take the background color of the scene. If not, we just take black, and then we clear the color to that. So we define that. Now, to store the color values of our shapes, we define a class called appearance that has a fill color and an outline color. The fill color starts off as being 0, black, with 0 opacity, so essentially there is no color. And the outline color starts off as just being white, perfectly opaque. And then we, again, redefine our polygon shape class to have an appearance. And by the initial value is just make instance appearance, and that takes the default values from the appearance class. So we define a couple of utility methods for ourselves. So kind of like we did for scale and translate, where we did it to the object and then let the object send it to its transform. We define a set fill color and a set outline color, and we apply that directly to the polygon shape, and we let that send it to the appearance in the right way. So what it does is basically it sets the color of the fill color of the appearance of the polygon shape to be color, and passes in the alpha key as to whether or not we're setting the alpha as well. Sometimes we want to like set the transparency as well. Sometimes we just say leave the transparency the way it is and set the RGB values. So we define these. And then we have to modify our draw method to handle this new color capability. So it gets a little bit more complicated because we're drawing each shape twice now. So first we draw the filled shape. And we say basically color is the fill color of the appearance of the polygon shape. If the alpha value is greater than 0, in other words, it has some opacity, then we draw a filled polygon. If not, we just skip it. If the opacity is 0, there's nothing to draw there. It'll be 100% transparent anyway. So what we do is we set the color. If you remember before, we had set the colors of our axes and set the colors of our marker drawer and things like that as being red and green. We set the color to the values of the array of the color. And I use the aref here to kind of like, say this is, we're storing values in an array explicitly and kind of like, using its elements. I could have just used the accessors red, green, blue, and alpha. And then we begin the polygon, which, drawing a polygon in OpenGL, which is a filled shape. And then we loop through all the points. We draw the XY of each point, and when we call end, the polygon is finished. And then we draw this, do the very similar thing for the outline. The only difference is that we take the outline color and not the fill color. Again, we check if it's got an opacity, and then we set the line width, and then we check whether we're doing, if it's open or not, just like before we did loop and strip, and then we draw the points. So the second half of this method is more or less what we had before, and the first half is drawing the filled shape as well as drawing the outline shape. So let's do some tests. We define a function that makes a group of hexagons for us. So a group of hexagons that are all scaled and rotated. And I did two versions of it. One, which is kind of more traditional Lisp style, I should say more classic Lisp style, where we do the usual thing of creating a list of shapes, loop for 10 times, can create an actual hexagon, some intermediate values, scale the hexagon, rotate the hexagon, push it onto the list of shapes, and then use that list of shapes to pass to make group to create the group that contains those list of shapes. And apply, oops, my phone, pardon me. There we go. Applies a given function to a list, but unrolls the list. Since our make group took an arbitrary number of shapes and not necessarily not a list of shapes, then make group kind of does the unrolling of shapes for us. But again, you can look it up if you want to know more about it. It's not a major thing. But so we can compile this if we want to. But I also did another version of it using the loop macro for those of you who are interested, where it may be a little bit more obvious from the code what's going on, a little bit more terse and brief and to the point. It's the same apply group, make group, but we loop for I from 9 down to 0. We'll see where we go backwards. For factor is I over 9, so this is creating a temporary variable. And then just collect the rotation of the scale of the make hexagon. And since these guys return the hexagon, we can kind of nest them in a more functional way, if you like. And the reason we go down from 9 to 0 instead of going down from 0 to 9 or from 1 to 10 is that the order of the shapes that are returned is important for our display purposes. Since we don't have three-dimensional graphics in this tutorials, we have 2D graphics. Any shape that's drawn first will be behind any other shape that's drawn second. So when we push each hexagon onto the shape, it's pushed onto the beginning of the list of shapes. Whereas collect puts things in order of the loop that you're doing. In typical Common Lisp idiom, you will loop and push things onto a list, and then you will probably return, if you care about the order, the reverse of the shape of the list. So we'll see the results of doing things in that order. So one of the first things we can do is basically set a background color for our scene. So now we have a nice, great background, already looking more professional. We define a square and add it to the scene. This is so far where we've been up to now. Now we set the outline color of the square to be yellow, which is 110. So now we have a yellow outline square. And we set the fill color of the square to be blue, slightly off blue. So there's our first colored shape. Yay, this calls for a drink. All right, pardon that interruption. We're back now. So we're going to create our hexagon group. And so what we can see here is basically it's a series of hexagons. Each one is scaled down in succession and rotated slightly as well. So the important thing is that the inner hexagon is the last one that's going to be drawn. So it's the one that's in front, so to speak. Now, if we assign random colors to them, we have this thing happening. So what we're doing here is we're basically using our doHierarchy function that we defined earlier, and we're passing it a function that sets the fill color to be a random color and sets the outline color to be black. And it's only doing it for the leaves, obviously, because the groups themselves are not subclasses of polygon shape. They don't have an appearance, so we can't set their color. So, and each time we reevaluate this, of course, since we're giving it random colors, it'll be so very psychedelic. I could sit here all night and do this. Now, we can do a similar thing here, but instead of passing random colors, we pass it random colors in a certain range between a darker and a lighter blue. So each one of these is just a shade of blue that's interpolated between 0.2, 0.2, 0.4, and 0.5, 0.51. So now what we do is we define a useful function called setGroupColor. And what that does is basically wraps up the doHierarchy stuff and the test is leaf for us, and just simply sets a fill color for us. So we can set, for example, the background to be black. And then what we're going to do here is we're going to set the color of the hex group to be a pinkish color, but with only an opacity of 0.1, so 10% opaque. And we set the background to be black so we can see it better. So you can see what's happening here is basically it starts by drawing the outside hexagons, and each one has an opacity of 10%, 0.1. And as it draws it, the opacity builds up so that over here in the middle, we're essentially looking through 10 hexagons, and therefore it's a brighter color, which is more opaque than it is on the outside. It's the same color, but with different transparencies, basically. All right, so that's our little introduction to colors. Now we'll try one more thing. If you remember at the beginning of the class, we talked about organizing generic functions in a certain way that might be useful. So here, what I've done is I've taken the generic function. So we basically had various levels of setting colors. We could set the colors directly on an appearance. We could set it on a polygon shape that would basically then send that color to its appearance, or we could send it on a group, which would use a doHierarchy function to traverse its hierarchy and set the color of every leaf node that it had. But now what we're going to do is define a general purpose, setFillColor generic function that has 4 methods inside it directly. The first method specializes on T, which, as we've seen, is the root of the entire class hierarchy type system, I should say, in Common Lisp. So in other words, if it can't find any more specific type, call this instance of the method. And we're basically doing nothing. We just declare ignore the color in the alpha so that the compiler doesn't give us a warning. And we're not doing anything because this is, if it gets called on something that's, for example, a shape, but not a polygon shape, and therefore has no geometry, has no appearance, it just ignores it. We have a method for the appearance class, which basically does the internal thing of setting the fill color to be what we pass it. Now, we've been a little bit clever here. The color that we're passing in can be an actual explicit color, i.e. an array of length 3, or length 4, I should say, or it can be a function that evaluates to a color. And what we do is when we get down to the appearance method and we have to actually set the color value itself, we check to see if the color is a function or not. So remember, the common Lisp has a type system, and you can check types of objects. So we check to see if the function is if the color is a function. If it is, we call the function color, and it will return a color to us that we then use. If it's not a function p, just use the color as is. If I was to be a little bit more diligent, I would probably call this variable color or function. It'll be a little bit more better self-documenting code, but I haven't done that. And then when we pass it to a polygon shape, it basically just calls the appearance of itself and sets the color to that. And then if we pass it to a group, it'll basically, the group itself has no color, so it doesn't do anything to itself. It just loops through its own children and then sets the fill color for each child accordingly. So this lets us use set fill color with a color or a color function on an appearance, a polygon shape, or a group. And if we ever have any other class that uses it, we just come here and add the case to this generic function. So we compile that. And then we have another set outline color, which is the exact same thing, same behavior. And now let's test these things and see how we can simplify a little bit the code that we were using before when we were setting the colors on our hexagon. So we make our group of hexagons again. And so now what we can do is very easily treat the hex group as if it's one object, and we just set it a color, and it'll take care of its internal color distribution, so to speak, whether it goes to an appearance or itself or to its children. So we set the fill color to be a random color, and we set the outline color to be black. I mean, I had done this before. This is the same thing again, but we don't have any do traverse, do hierarchy methods or anything like that in here. This is much simpler to understand what's going on, better level of abstraction. So now what we can do is do the same thing, but we also give a random color value to the outline colors as well to make it even more psychedelic. And then we do our shades of blue thing as well before. And finally, we end with our image of the translucent shades of pink. And the final thing we'll do is we'll set the outline color to have opacity and alpha of 0. And that will take away the black borders, and we get this nice little graduated shape. So that was lesson 7. We'll do some more color experiments in lesson 8. Thank you. Welcome to our first corrections installment, wherein reviewing the video, I realized that I was saying some stuff that made no sense whatsoever. So when we were looking at the sealer, the interpolation of 2 colors to give a third color, return a color, I said I didn't know if the map function returned a value or not, and it didn't matter in our case. But of course it matters a lot in our case because we're returning an array, which is the interpolated color. So let's look at a little bit in more detail what this does. So just going to reformat it for clarity's sake. So map takes a type, which is the type of the sequences that's sequence or sequences it's going to iterate across. It takes a function to apply to each element or elements of those sequences, and then it takes as many sequences as there are arguments in the lambda. So we're giving it two colors. These are arrays of length 4, and we're giving it a function that takes two values, which are going to be our float values. So basically, it's going to take the 0th element of C1, the 0th element of C2. It'll do a linear interpolation. This returns a real number, and then that number gets accumulated in the output sequence as the element at the index 0, and then same thing happens for index 1 and index 2 and index 3. So map, of course, returns a sequence of the same type as the sequences that it's consuming, and that is essential for this function to work. Same thing down here, when we add two numbers, all we're doing is adding the elements at each index of these two values, C1 and C2, and then it's making an array out of those. And we're able to do this in this convenient way because we defined our colors to be vectors, i.e. arrays of dimension 1. So that's kind of one of the consequences of choosing that implementation, that we can do things like this. All right, thank you for bearing with me. That was the end of our first errors section. Hello and welcome to our second errata error correction video, hot on the heels of our first error correction video. So looking at the code here, it occurred to me that I need to drink something way stronger than decaf coffee if I'm going to write the code well. So if we look at this function here, adding two arrays element-wise, this is way too overthought. All this needs to be is map array, the plus function, C1 and C2. That's the whole point of having, one of the points of having an array as our data representation. Easy to just traverse through it. Compile that. Similarly, for the jitter one, all it needs to be is apply the function rand1 to the color delta, and then add that to the jitter. So thank you again for bearing with me while I make my silly mistakes in public, and we'll see you next time. Bye.